Well, good morning, everybody, and welcome to today's webinar, this morning's webinar, titled Gaining Insight to Product Performance. My name is Rob Romanowski. I'm the Director of Operations for 3HTI, and I am joined today by our Senior Engineering Director and Analysis Leader, Mr. Bill Stickney. Boy, that's a mouthful. So anyway, we hope everybody's doing great this morning, having a happy Friday, and we're really excited that you could join us today. So before we get into everything, just a couple of housekeeping items. Everybody, just like most webinars that you've been on, you're going to be on mute. And if you have any questions, feel free to type them in the dashboard of your Citrix GoToMeeting dashboard. And we will try to answer questions during the presentation, but most likely they will be answered at the end during the Q&A session. So we're hoping to get everything wrapped up within a half an hour, 35 minutes at the most. Also, if you look in handouts, there is a PDF brochure on Creo Simulate for your viewing pleasure. So with that, let's get started. Real quick, just something about 3HTI. In general, our mission is truly to help people live better lives, and ultimately we do this by helping our clients create better and more innovative products. And we do this by improving a company's competitiveness related to product lifecycle management by providing a myriad of technology solutions and services to help them adopt and maximize these technologies. And that allows them to develop and manufacture products better, faster, in a more cost-effective manner, and ultimately improving the profitability of their business. So we have a major focus on software solutions and product lifecycle management with CAD, CAM, and computer-aided engineering, as well as providing a whole litany of services. Our contract engineering services can be done either on-site or off-site. We've run into quite a few situations where customer needs to get something done quickly, and they don't have the time to implement the software or learn the software, so they'll just turn it over to us, and we can either do it for them or work alongside of them. We're pretty flexible in that respect. In addition to being a reseller for PTC products, which is one of the products we're going to look at today, Creo Simulate, we are also a reseller for several other systems within product development. One being a whole host of Mentor Graphics solutions, and we have been named the Gold Partner of the Year for Mentor Graphics for 2015, which we are very excited about, being the #1 reseller in North America. And similar to what you're going to look at today with Creo Simulate, Mentor Graphics products also give the designers and engineers the capability of using a very sophisticated tool in an easy manner to find sophisticated results. So it's an easy tool to use, but provides sophisticated results. In addition to these analysis solutions, we are also a representative. We're the #1 reseller in the world for Mark-forged 3D printers, which prints in carbon fiber, Kevlar, and fiberglass, which is pretty cool. Stratasys printers, as well as Steinbichler scanners, and a host of other solutions for machining like NC Simul and Multi-DNC, Keyshot for rendering software, and Controls Pro Studio has a configurator which allows you to take a design and let your customers see it in different iterations pretty quickly and easily. It's pretty cool. Here's a host of customers that we have done business with within the past year for most of these. Some of these are longtime customers, and if you notice, some of these names are almost like the who's who of, within their industries. But that's not to say if you're a smaller or mid-sized company, because we have a lot of smaller and mid-sized customers also. Whatever the size of your company is and whatever your problem is, that's what we want to solve. So it doesn't matter how big your problem is or how small your problem is or your size of your company. We're pretty flexible in how we can help you out. Now, what I want to do at this point is I'm going to launch a poll here. See how crafty I can be here. So the question of this poll goes along with this slide. why are most designers not using simulation? In some cases, it might not be required by your company. Some people believe that the software is hard to use or an expert that's required or it's too expensive. So right now we're asking, are you currently using simulation within your company? And if you are, what type of simulation tool are you currently using? Boy, you guys are good. And the next question that kind of goes along with this slide, what is your impression of simulation tools? Is it that the software is hard to use? Is it that it's too expensive? Would you need to hire an expert to be able to use an analysis tool? Are you under the impression that they help design a better product? And you can pick more than one answer. Also, if you're not sure, that's also a selection too. But through the Aberdeen Research Group, what they found is that best-in-class organizations are 70% more likely to implement a get-it-right the first time strategy, as well as analyzing product behavior earlier in the design process. And that's basically what we're trying to do. We're trying to help our customers, our clients, build a better product with tools that are easier to use earlier in the design stage, so that even if you are using a high-level design tool like, say, Abacus, you can use a product like Creo Simulate early in the design stage, so by the time it does get to the analyst, everything's going to be verified, and you're really it's not going to come back to the designer or to the engineer. It's going to continue to move downstream and save time and get that product to market faster. So once again, unlike most computer-aided engineering solutions, Creo Simulate does not require the user to be an expert in the field of analysis. And the solution, once again, was created to give engineers the tools they require to analyze these designs early in the process and use those results to influence and drive design decisions. So this allows your designers and engineers to focus on the designs and let the software focus on the calculations. These are some of the capabilities of Creo Simulate. And once again, in the downloads folder in the dashboard, feel free to download the Creo Simulate brochure that's in there. But as you can see, it handles a whole host of capabilities, and I'm going to let Mr. Stickney talk a little more in detail about these during his presentation. So a little bit about Bill Stickney. Bill's been with 3HTI a little over 10 years and has over 30 years experience in analysis. He worked for a long time with a company called Instrument Specialties, which is the former name of Laird Corporation. More recently, he has worked on projects with 4 different NASA space centers, and he's been there on multiple occasions. So it's nice to get invited back, Bill. I'm glad you're on your best behavior. Also, he has done projects recently with Merck Pharmaceuticals, ITT, and High-Vac trucks. So Bill, I am going to pass you control, and we will be able to see your screen, and you can start the demo.
Okay, Rob, are you able to see my screen?
I see your screen connected to GoToWebinar.
I need to show you my other screen. Hold on.
So you're like me, Bill. You have 3 different screens?
2, actually. Can you see Creo now?
Yes, we see Creo
Goody.
Parametric. Excellent.
All right, we're good to go. Okay, well, what I'm going to do today is show one of the advanced capabilities of Creo Simulate. Creo Simulate is typically marketed toward designers because it is one of the easiest to use of all the FEA tools. It is very forgiving and will generally give you a solution even if you don't do it very well, which is probably useful information. Now, one of the problems that we often run into in FEA is figuring out how to constrain parts. And usually if I find people that have made erroneous results, it's because they over-constrained or somehow didn't properly constrain a part. So one of the solutions to that is to do the analysis in assembly mode where the parts are realistically mated to their mating parts and you're analyzing the whole works. So any bad assumptions are far enough away from the area of interest that it's not going to affect your conclusions much. And that's what I'm doing here. This thing is represents a ball bearing installation. And you see this part here that's kind of in an orange color represents the outer race of a ball bearing. And it is installed in a housing. Now the bearing, of course, is made out of steel. The housing has aluminum material properties right now, but of course you could use any other material if you wanted to. This is a quarter symmetry model. We're only analyzing 90 degrees of this bearing, and the presumption here is that this stiffening rib, there's going to be 4 of those, and they will be exactly opposite in the other 3 quadrants. This is a very common technique that's done a lot. It cuts way down on solution time, but also it allows us to visualize the data a lot easier, and it also allows us to constrain the parts a lot easier. So it's a common trick. It's certainly not unique to Creo Simulate, but it works here. What's a little interesting here is that this is a press fit problem. So this bearing is actually larger than the housing. The bearing, by the way, I think is about 1.6 inches in diameter, and it interferes with the housing by 1/1000th of an inch, which would be like a 1/2,000th per side, which might be a reasonable fit for a bearing. So what we're trying to figure out is what's happening to the housing and what is happening to the bearing race. And the housing you might think would be of more interest, but it turns out that the results actually show some interesting things with the bearing as well. One thing you know for sure is that nothing is really rigid. So assuming rigid behavior is probably dangerous, and we want to avoid it. So what we're going to do here is a deformable body contact analysis. We actually have these parts modeled so they are interfering, and when we do the solution, it is going to resolve the interference. So it is going to squash the bearing race inward, and it is going to squash the housing outward until they are basically in contact and there is no more interpenetration. Now there's other ways of doing contact. You can have gaps that close, and contact area varies with force and things like that. This is nonlinear analysis. It is very much statically indeterminate, because if you tried to do a basic statics problem here, you would not be able to get an answer at all, which is good reason for using FEA. So the trick here is we're trying to get realistic behavior, and in some cases you might also want to know what the contact pressure is or what the contact area is. That information can be obtained. What I'm really interested in here is what's happening to the housing, and do we have any problems with the bearing. So contact has typically been the domain of high-end product. It is, however, works fairly well in Creo Simulate, assuming you're doing this deformable body contact in 3D, which is the only, actually you can also do this in 2D, I should be specific there. And in fact, a problem like this you might want to do as a 2D axisymmetric problem. The only problem here is the stiffening rib makes it not axisymmetric. Otherwise we would do it in 2D and it would solve a lot faster. So what I'm going to do is set up the problem, and then we'll show you some results. And this is not particularly difficult to do. First off, I'm right now in Creo, so I built my assembly in Creo on the modeling side. And now we're going to go into Simulate. Simulate is the FEA environment. So you'll note that the ribbon up on the top now has all kinds of analysis features instead of modeling features. We have material already assigned in this case, but that's one of the things you would have to do. Material is linear in this case because we are presumably not going to squash this far enough to break it. If we find that's true, we would redesign it. So one of the things that we know in analysis is you need to have good quality mesh. You want nice, uniform, shaped, and spaced elements. And it's a good idea to preview your mesh to see what you're going to get here. Now, in fact, you wouldn't necessarily have to do that to get a solution, but if you want a good solution, you probably do. So I'm going to preview my mesh, and then we'll show you how to deal with it. The preview button would be here. This is going to create mesh. Now, this isn't going to look good initially, guys, but we're going to fix it. Don't worry. Creo Simulate uses a technique called p-elements, which is a variable edge order. For example, in traditional H method analysis, you would have either first or second order elements. Second order elements would have mid-side nodes and would have parabolic shapes. These are in fact third order elements, have two mid-side nodes, but they can go higher. If the solution finds that there's a lot of gradient, a lot of change, for example, in stress over a small area, it will increase the edge orders in that location, which is almost the same thing as remeshing with finer elements, but it does it automatically. In reality, you have to do some of both, because this is not very good mesh. Anybody that's a VA expert will look at that and probably turn funny colors and say, no way that's going to work. Well, we'll fix it. So I'm going to do some mesh refinement, and the good news is it doesn't take long. It's very fast. You can mesh something and get decent mesh in a matter of 5 or 10 minutes in this product. So let us do some mesh refinement. What I'm going to do is put some controls in here. And this would be a AutoGem is the name of the mesher. But the control I'm going to put in here is going to be limiting element size, and I'm going to do it by component initially. So I'm going to pick a component here, and I've done this problem already, so I know that the correct size here is about 0.32 inches. Sometimes takes a little trial and error to get this to work right, but that's not so unusual. Now, the bearing race being smaller, and particularly being a contact item, should have much tighter mesh than that. So I'm going to assign it mesh of 0.08 inches. And in fact, one might go smaller than that, but turns out this is about as small as you want to get with a reasonable solution time. So now what we can do is take a look and see if this mesh is better. So we'll create mesh again. The mesh, by the way, is not stored. It's created on the fly when you run the analysis. So what we're really doing here is creating rules on meshing rather than actually creating elements per se. So what we see here is that the element quality is much better. Now these are tetrahedron elements, and an ideal tetrahedron would have equilateral triangles on all four faces. The previous case, we had a lot of elements that were very long and skinny and had bad aspect ratio. Now you see that has improved greatly. This is reasonably good mesh at this point, good enough for what we're doing in any case. The bearing is rather good mesh. If you look at that, there's not too many long stringy elements or bad transitions. We have nice clean mesh, and we didn't have to do much to get it. So far, so good. Now the next thing is the transition, or we actually want tighter mesh on the mating face of the part here. And the transition area around here is not great, so we actually want to tighten up the mesh in that area. We don't have to tighten the whole unit though, because that's going to waste a lot of computation time. So what I'm going to do here is a technique which is to make a region And I'm going to use a volume region. So basically we're going to chunk a part out of this thing and give it different mesh properties. And this is one of the standard techniques for mesh refinement in Creo Simulate. So make me a volume region. I'm going to do it on this component, and I think that's okay. And then I'm going to pick a sketch that I already have in here, although one could make a sketch on the fly. So there's a sketch, and what I'm going to do here is just extrude this through, all the way through the part in both directions. You wouldn't necessarily always do that, but typically what we would do. So now I have created a new region, and you'll see the boundaries of that region are now showing up as edge lines here. And what I'm going to do is give that tighter mesh properties than the rest of the housing. So now we get good results close to the bearing without getting excessively large mesh or too many elements. I guess you can't have too many elements other than how long you want it to run. Now this will be a volume and not a component. So here's a volume, and we'll give that a size of 0.2 inches. And then we can see what that looks like. And let's mesh it again. It's a good idea to always check your mesh, make sure it's going to work. It's pretty robust. It meshes just about anything, but quality of mesh, of course, is an issue, so we don't want to ignore it. Well, now I'm getting a lot better mesh in this area here without doing a whole pile of work. But I would still like to have it even tighter where it is contacting the bearing. So I'm going to do one more region on the thing. And this case here, I think I will open the part in its own window, which is an option. Probably the more typical way to do it. So I'll open this guy here, and I'm going to make a region right around that bearing race with tighter mesh. Again, I could just mesh the whole thing tighter, but it would run slow if we do that. So we don't want to make it run slow. Turns out that the more times you run it through the analysis and the more things you try out, the better your design is. The longer it runs does not give you a good design. Trying ideas does. So let's see. I want to now go in and do a volume region here as well. This one I'm going to sketch on the fly just to show a different workflow. So I did not already have a sketch here. So I'm going to sketch it on that plane there. That's okay. And this is a very simple case here. All I'm going to do is sketch a quarter of an arc. Let's see. I can use the center arc so we know where the center is. So our arc would go something like that, and this should be a closed volume for this feature. So we just close this up, and this is just like sketching anything else in Creo. It's really nothing terribly complicated. And its radius should probably be about 0.8 probably. Something like that. Now a little bigger than that. Let's make that about 0.88. There we go. Okay. So again, this extrudes through the part in both directions all the way through. And now we've got modified part. So now I go back to the assembly and let's mesh it and see what it looks like. Actually, I do need to assign mesh properties to that region now. And we'll probably have to regenerate it as well. Okay. And I'm going to do the same thing. I'm just going to assign element size control. Now, there are other ways of defining mesh refinements, but this is the easiest. And it works about 99% of the time. And it's probably about all you got to do. So you cut some regions and you assign some different element sizes and you get better mesh. Requires a little trial and error and some judgment. And you may want to run it once and see where the high stress is before you finish the refinement, which of course is how FEA is traditionally done in the older products. And now we got good mesh. So I've got fine mesh on the bearing race. I've got fine mesh on the housing. I've got a decent transition from the fine mesh out to the coarser mesh. So I've got good quality elements where I need them and decent mesh everywhere else without making the model excessively large. That's pretty much the objective of mesh refinement. So we did this whole thing, and it took probably less than 10 minutes or so. So we're almost ready to run it. What we need to do now is to define the boundary conditions and particularly the contact interface. So we'll do that next. The interface selector. And what we're going to do is make instead of a bonded interface, we're going to make a contact interface. So this is deformable body contact. This is where the contact area varies with load, and it is nonlinear. I'm going to do it component by component. That is usually a more robust method if you can do it. So here's my first component, here's my second component. Now there are cases where you may want to pick the surfaces individually for making contact. This is simple enough we don't have to do it, and very importantly, by choosing component, it's going to pick up this fillet out here, which is actually a good thing. You don't really want contact surfaces with sharp edges. So that's actually going to help us. All right, our minimum distance here I'll say is 2,000. So anything that's closer than that is considered to be in contact. Now in fact they're in interference, but it's within that tolerance. And the only other thing we would have to do is decide what to do about friction, and it turns out that for an interference problem we actually want to set infinite friction, which means that the bearing race is not really moving relative to the housing, it's just squashing and changing radially but not in other directions. Now if you're using other materials like elastomers, this would not be correct, but it's the best way to do it here. So that's all we have to do to define contacts. Very little to it. So we now have contact. Now we have to be concerned about boundary conditions. So one of the boundary conditions we would put in would be symmetry. And we have a displacement maker here. So here's a displacement maker. We'll pick surfaces here, something like that, to define symmetry. And actually, locking them in the X direction would be the same as symmetry. We do have a symmetry constraint specifically, but it doesn't do anything different than this. So we would wind up doing the same thing on the bottom face in Y, and then we would constrain probably the outer rim here in Z. Maybe this guy here and that guy there in Z. All right, so now that plate is constrained. So what we've done here is eliminated all the rigid body motion in the outer housing. The bearing race is captivated by the symmetry boundaries here and down here, where we would have to make one. And it's basically locked onto that housing, except that it is actually not really constrained in Z. And if you were to run it this way, it would probably give you a rigid body error. So what I have to do is attach the bearing race to the plate. And the only purpose of this is to eliminate rigid body mode. So we would come in here, and I'm going to make a spring element just to get a connection between the two. And this basically isn't carrying any load, it's just to satisfy the solver. So we'll do this. I'll go into here and put a spring element in here. And its stiffness is almost irrelevant because it's really not moving, so we'll just put in a very low stiffness. It's in pounds per inch. Bearing in mind it's not moving very much at all. So now I have attached the bearing race to the housing. Now the problem here is we don't really know what that housing is doing. we're kind of assuming that it's just going to sit there and change in the radial direction, but that's not necessarily a good assumption. So you got to be very careful not to over-constrain a model on your first go-around. All right, so this thing's basically ready to run, other than putting another symmetry boundary on. And what I'll do now is just skip ahead and show you the results in the interest of saving some time. By the way, it would be quite capable of running without the mesh refinement. It would give you a solution, and the displacement solution would probably be pretty good, but the stress solution might not be the best. So some mesh refinement is usually a good idea, and considering it only took us like 10 minutes to do it, it is well worth your while. So the bad news is you may still have to do some mesh refinement. Good news is not too picky and don't take long. So let's look at results now. So what I want to do is, by the way, this model with this level of mesh takes about 3 hours to run. So contact analysis is not fast, and that's true of everybody's contact analysis. That is not a problem unique to Creo Simulate. That's why we like to do these problems in 2D if at all possible. But it's not here because of that rib. So let's take a look at the results. So I'm opening up results now. And first thing let's look at is displacement and see if that looks reasonable. So here's our displacement. Now it's very curious because we know that the interference between the housing and the bearing race is like a 1/1000th per side, yet I'm getting displacements of about 1/1000th. So that seems a little odd. However, we're looking at magnitude here. So what I want to do now is resolve this down so we're looking at, let us say, the y direction of displacement. And now you see the displacement is more like it's expected. So negative means downward in this case, so the bearing race is moving downward by about 3.5 times 10 to the 5th, which isn't very much, and it may be fine. The housing's moving about 10 times further in the other direction. So the housing is clearly more flexible than the bearing race, and that's not too surprising. It is aluminum, so it's a lower modulus material to begin with. And also, you see that the outer rim here is moving further than the part where the web is. Now, we can visualize this better if we do a little deformation. So I'm going to go in here and make this deformed. I'll give it a scale of 100 to 1, although in large displacement analysis, we frequently do it at 1 to 1. So very interesting what you see. It turns out that as this rim tries to expand bigger, it's taking this plate and rotating it clockwise in this view, because we have larger displacement on the tip of the plate than we do at the root, and it's kind of bulging or bowing the whole side of this this flat plate here. So the whole thing's moved in Z. That's probably not real intuitive. I wouldn't have guessed that. But now we know. We also know that the bearing is moving in a nonlinear fashion as well. One side of it's squashed more than the other side. Now, is it enough to cause trouble? That's where we need to do some engineering judgment. Not sure about that. If you're concerned about the quality of the solution here, we have the ability of showing the mesh, which is probably a good idea at some point. So that's what our mesh would look like there. And you see the elements in the contact area are pretty good elements, so we think we got a decent solution here. Another thing you would look at is probably stress. So actually I'm going to, I guess I can leave the displacement on. I'm going to turn on stress, and we'll look at von Mises stress. Since this thing is kind of round, it's going to be the easiest to get information out of. So here's what stress looks like. And what I am interested in is I would really like to see a nice smooth fringes here. I don't want to see jagged looking shapes on these color bands. So those look pretty good. I think it's a decent stress solution. So we're not in bad shape there at all. Now we would also probably like to look at contact pressure. So to do that, I'm going to have to turn off one of the parts so we can see the joint between them. So we'll go back and turn off deformation, and I'm also going to hide one of the parts. So we'll go in here and let's hide the, I guess we'll hide the housing, although either way would work. And what I want to look at here is actually contact pressure. It should be here. So we do an OK and show there. And why am I seeing both parts? I must not have done it quite right. Bearing housing part. Curious. Well, let's try turning, no, that should do it.
Well, the thing that our audience should know, Bill, is the way that we operate. We're not like a cooking show where we, you don't see all the prep work ahead of time. You know, you just see that this, everything thrown together, and then they put it in the oven, and then they turn out what they've been cooking all morning. This is live.
Well, that's, yeah. The display is live. The runtime was not.
True.
Actually, when I do training, I like to use the customer's own hardware, if at all possible, because things go wrong and then you learn how to fix them. Criticism of most training curriculums is that everything always works right, and it doesn't always do that in real life. So this is very interesting. This is the contact pressure on the bearing race. So we see it's uneven for one thing. We've got higher pressure on one side than the other, but that's because of the asymmetry in the location of the web portion of that housing. Not necessarily a problem, but this is curious here. You'll note that in the center right here, we're seeing a larger pressure than we do out in this area here. So what's happening here is where that rib is, right opposite the rib, we've got a little bit of a tight spot in there. And it is actually squashing that bearing harder there than it does elsewhere. And the implication of that is that it's probably squashed the bearing to the point of being out of round. So that bearing is kind of a squashed into a four-sided shape now. Now, it's not a lot, and if you need to know it precisely, we could put measures in and we could measure the displacement of that center relative to the outer edges. And then you could determine whether or not that's an acceptable condition for that bearing. But what's curious here is that we see that the bearing is no longer of the original shape, and it's actually potentially got a big problem here. So maybe putting ribs on that race was not such a good idea at all, and maybe we ought to do that differently. But now we know, and it didn't cost us a whole pile of time. So it's taken me, what, like a half an hour here to set up the example. Ignoring the three-hour runtime, within an hour we know exactly what we got, and now we can improve the design. And we could do this very early in the project before we put a lot of effort into it. All right, so the only thing I haven't shown was the actual setup of the nonlinear analysis, but and we're getting short on time, so I think I will omit that. But it's not particularly difficult. We're just building a static analysis, declaring it to be nonlinear, and turning on the contact interfaces. Okay, Rob, I think that's about all we got time for.
Sounds good. Hey,
And we
Bill.
got pretty pictures.
Very pretty pictures. It is now Q&A time, and we do have a couple of questions coming in. So the first question, Bill, is how well does this handle gaps where contact is expected due to bad model creation?
Um, I think that question is referring to the meshing and how parts are interacting in the assembly. I don't think that's really a deformable body contact issue, because those deformable body contacts handle gaps just fine. The answer is not particularly well, because the normal interface between parts in an assembly would be usually bonding, and you have to have a good fit to get it to bond. So if you've got, for example, on a weldment, you've got grooves, that are cut in to accommodate weld material, things like that, it is basically not going to connect those together. So we're going to have to make some modifications to the geometry to get that to actually be meshable. And that would, one technique for doing that, by the way, would be to make a merge part where you can actually have interference between the parts and it will resolve them. If there is interference and it is not a contact issue, then there's no problem. The parts simply occupy the same volume, and that's okay. So that is an issue. It is very common to have to do tweaking to the model to resolve those kinds of issues. Now, we do have a tool in Creo called flexible modeling that can help you do that without having to go back and make changes to the parametric model. So I wouldn't say that it automatically deals with those issues easily. There are other products where you can put in a tolerance for merging mesh. This does not work that way. Other question?
That seems to be the only question at this time.
Okay. Well,
so Bill, I
don't
did like
the
explanation of the P element mesh.
Yeah, let me show you one thing on that. I'm going to turn on the other part back on, because I can show you what the P levels look like here. That's one of the options, and that's one of the tools you use to diagnose whether you've got a good solution or not. And this, I think Creo Simulate's the only commercial product that uses P-mesh. It's been around for quite a long time. So what I'm going to do out here, instead of showing pressure, we'll show P-level. And it turns out this is a pretty good model. The primary color that you see here, this cyan kind of color, is a third order element, which is a pretty good element to begin with. And what this is shown here with these other colors in this area is that in the region of contact, where we have a lot of force and probably stress, it has refined these elements and given them higher edge order, up at this looks like order 5 or 6, probably 5, I think. And we have effectively done mesh refinement on the fly without having to do mesh refinement. Because the alternative would be to go in and tighten up the mesh on those regions where we put small mesh to begin with, and the solution time would now go probably in double if we were to do that. So we've effectively accomplished mesh refinement without doing any work and without excessively increasing solution time. And that's what these elements are. They are good at taking mediocre mesh and turning it into a really good solution. Not that this is necessarily mediocre mesh, but the point here is that you're using a combination of two methods. One is just using good judgment on meshing, and the other is the P element refinement. And between the two of them, you get a very nice solution.
We have a question asking if you can show the volume setup for regions in the aluminum part with more dense mesh or less mesh.
Yeah. Let me show that. I got to go back to the FEA model. So there were two things I did here, and I want to make sure we're clear on this. I made regions in here, but I also applied mesh controls. So this control right here, for example, has limited my element size to 0.2 inches. All I got to do is change that number. I get a different mesh in there. So for example, I'll do it on the inner one here. This is limited to 0.08 inches. If I edit definition on that guy, let's make it maybe 0.05 and remesh it, you can see the results. So the important part of this is the mesh control that I put in limiting element size. The lesser important part is the volume. Now the volume in fact does result in some mesh refinement. The combination of the two is what you really want. So this is taking a lot longer. There's a lot more elements in here now. Alright, so that doesn't look different. I might not have done that quite right, but it should have put tighter mesh in there. I'll go back and look at that again. I might not have saved it right. No, I did. Well, I'm not sure why that's looking different. Unless I did the bearing race instead of the aluminum, that could be. But the important thing here is that it is these controls that are creating the tighter mesh, and that control, the maximum element size, can be applied to surfaces or volumes, which is a subdivision of a part, or it can be applied to a whole component, which we did with the bearing race. You can also do them on edges. That would be applicable if you were doing 2D or shell elements. By the way, you cannot do contact problems with shells in this package. You can do a lot of other things with shells, though. All right, do we have other questions, Rob?
I think that is it.
Goody.
Excellent. So I'm going to take control back. Just let everybody know, if you want to get in touch with us, if you want to see a demonstration of CryoSimulate on something, a product or a part or an assembly that you specifically make for your company, let us know. We would be more than happy to spend some time with you to solve that and figure that out for you. This is the way to contact us. You can call us toll free at 866-624-3HTI, or you could contact me. You could call me directly or send me an email. Either way, we'd be more than happy to help you out, answer any questions that you have. So, Bill, thank you very much for doing a great job today, as always, and I'd like to thank everybody for attending today. If you need anything, please contact us. Thanks again, everybody, and have a great weekend. Take care.